Imagine a student taking a massive semester-long exam. Every single answer they give actually changes the questions that come next. So how on earth do you grade them? Do you wait until the very last day and just hand them a pass or fail? Or do you hover right over their shoulder, grading literally every single keystroke? Well, this exact dilemma is what AI researchers are wrestling with right now when trying to train autonomous agents to handle long, complex, multi-step tasks. Welcome back to The Explainer. Today, we're diving into a really fascinating breakthrough. We're looking at how to train large language model agents to navigate complex, open-world environments without, completely losing their way. And the paper we're unpacking today introduces a totally elegant solution to this very grating problem. Before we get into the nuts and bolts, we absolutely have to credit the powerhouse team behind this. The paper is titled Self-Distilled Agentic Reinforcement Learning. It was authored by Zhengji Liu, Zhuan Yao, and a fantastic collaborative team across Zhejiang University, Meituan, and Tsinghua University. Honestly, they've taken on one of the most stubborn hurdles in agentic AI right now. Okay, here's our quick roadmap for today. We'll start with the multi-turn problem, then move into the SDR architecture, cover why SDR actually matters, and wrap up with some real-world applications. All right, part one, the multi-turn problem, and the big challenges in AI training. So let's dive right into this. Why is training multi-turn agents so incredibly hard? Right now, we basically have two main training paradigms, and they're kind of pulling in opposite directions. On one side, we have reinforcement learning, or RL. Think of this as the teacher who only grades you at the very end of the semester. You get a reward if you succeed, but man, that signal is super coarse for a long, complicated task. Then, on the flip side, we have on-policy self-distillation, or OPSD. This is the teacher watching your every move, giving dense, token-level feedback from a teacher branch that has access to all the privileged context, like retrieved skills or the literal answer key. Now, you might be thinking, why not just combine the two? Seems like a no-brainer, right? Well, bringing OPSD into multi-turn environments is actually super problematic. If you look at this graph, you can see the green line absolutely plunging. If you try a naive approach, just slapping RL and OPSD together, performance just falls off a cliff. The researchers call this multi-turn OPSD instability. As the agent makes moves over multiple turns, it inevitably drifts away from the teacher's ideal path. When that happens, the token-level advice gets unreliable, the errors start compounding, divergence goes through the roof, and the agent's success rate just tanks. And that brings us to a really crucial concept the authors identified: asymmetric trust. See, in this scenario, the teacher isn't actually some smarter, bigger model. It's the exact same model, just given extra privileged info. So if the teacher agrees with the student, awesome. That's a positive endorsement. The student is definitely on the right track. But if the teacher rejects what the student wants to do, well, we actually have to be pretty careful. The teacher might be rejecting a brilliant idea just because the extra info it's relying on is irrelevant or flawed. The researchers realized they needed a system that heavily trusts positive endorsements, but takes negative rejections with a huge grain of salt. Moving on to part two, the SDAR architecture and how they built a gated solution to fix this. This realization that you can't always trust the teacher meant that pure RL had to stay in the driver's seat, while the OPSD feedback needed a leash. Enter SDR, which stands for Self-Distilled Agentic Reinforcement Learning. It beautifully unites these opposing forces. It keeps standard RL, specifically GRPO, as the main unbiased backbone, but it brings in OPSD as a gated auxiliary objective. Now, what's really interesting about this framework is how it flows. On the left side of the diagram, you've got the agent loop actually interacting with the environment. Over on the right, the GRPO module is busy calculating big-picture advantages based on the final task outcomes. But the real magic, that's happening right in the middle block, the OSPD module. Instead of forcing the student to blindly copy the teacher word for word, SDAR introduces this brilliant token-level gating mechanism. It looks at the gap between what the teacher predicts and what the student predicts, and then it pushes that signal through a gate. Let's break down those mechanics. Step 1, keep RL as the main optimization engine. Step 2, compare those probability gaps between the teacher and the student. And step 3, apply what's called a sigmoid gate. This gate is basically a mathematical function that takes that raw gap and turns it into a smooth, bounded weight between 0 and 1. If the teacher really loves the student's choice, the gate swings wide open, pouring on the guidance. But if the teacher disagrees, a negative gap, the gate softly filters that advice out. It literally stops those compounding errors we just talked about right in their tracks. I absolutely love how the authors summarize their core philosophy here. They said, let each token decide the intensity of its own supervision. Think about how profound that is for a second. Instead of some rigid, hard-coded schedule for when to listen to the teacher, the AI builds a dynamic, self-paced curriculum at the absolute finest granularity possible, token by token. All right, part 3, why SDR matters, and the kind of performance we're actually seeing. So, the million-dollar question, does this elegant math actually work in the real world? Oh, absolutely. The accuracy jumps are massive. On a super complex e-commerce benchmark called WebShop, using a 7 billion parameter model, the SDR architecture bumped accuracy up by a whopping 10.2% over the baseline GRPO model. It also scored a 9.4% boost on embodied control tasks and a 7% boost on multi-step search QA. And crucially, it completely avoided that catastrophic crash we saw earlier with the naive hybrid models. But honestly, the most mind-blowing part is how robust this thing is. The researchers say SDAR degrades gracefully with retrieval quality. What does that mean? Well, they tested feeding the teacher completely random, totally useless skills. And guess what? Even with random, garbage retrieval, SDAR still outperformed the pure RL baseline. No way, right? The gating design is just so incredibly good at filtering out the noise that it only absorbs the helpful stuff. And when you track the training dynamics across these different environments, it proves something really important. The agent isn't just faking it or using the privileged context as a crutch. Because it selectively filters the advice, the student actually internalizes the knowledge deep into its own parameters. It learns to stand on its own 2 feet. So when it's out in the wild, doing inference without any external help to lean on, it performs exceptionally well. Finally, part 4, real-world applications and what this means for the future of agents. Taking a step back, the environments they used for testing aren't just academic puzzles. They are direct stand-ins for the dynamic, open-world tasks we desperately want AI to handle for us soon. ALFWorld is embodied control. Think smart home robots navigating your physical spaces. WebShop is e-commerce automation, like telling an agent to autonomously navigate a website to find and buy you the perfect laptop. Search QA is an agent acting as a deep dive research assistant. And this all extends to general GUI automation. We are talking about having an AI operate your computer exactly like a human would to get everyday tasks done. By solving this multi-turn instability problem, SDAR proves something huge. AI agents do not need perfect supervision to learn complex, long-horizon tasks. They just need the ability to smartly decide when to trust the guidance they're getting. So it leaves us with this really exciting question. What does the future of autonomous agents look like now that they can essentially self-correct and learn flawlessly even when their teacher is completely wrong? I'll tell you one thing for sure, the capabilities of the next generation of AI just got a massive, highly efficient upgrade.